so far we have seen different testing techniques for circuits and circuits, so that the objective function that we had was to ensure for high fault coverage. Then sometimes we wanted to generate minimum set of test pattern, minimal set of test pattern, so that the storage requirement is less, then the fault coverage is high and the test time is minimized. So, in the sense that the time that we have in applying the test pattern, that is minimized. And for the techniques, we have seen that these ATPG tools, they can generate compact pattern set. So, that is one process. Then we have seen these compression mechanisms by which we can compact the test patterns, we can compress the test patterns and also compress the responses, and that way we can reduce the amount of information that needs to be stored into the system. Now, the point is that with the as the technology is advancing, so we are putting more and more device into the system, and as a result the other issues are becoming more important than say pure test length or test time duration. So, the other issues in that are becoming more important are the power consumption that occurs during testing, and also the type of temperature rise that occurs in the during the testing or during testing of the system. Now, what happens is that in case of design part of it, design engineers, so they are bothered about power, they are bothered about temperature, but they have got many tools in their hands. So, they can do something so that some part of the circuit is made to kept off. They also ensure that the several parts of the circuit, they do not operate simultaneously. So, that way they can take care of this power problem. However, when we are having this testing, so it is not always the case. A test engineer may tell that okay, these parts should not be done together, or say this part they should have a separate power supply or separate frequency of operation. So, that may not be possible from the design angle. So, the with this increase in the complexity of testing, so power has also become an important issue. So, in this part of the lecture, so we will try to see how this low power can be ensured during the test operation. So, revolution in design paradigm challenges both design and test engineers. So, revolution has occurred because now what has happened is that complexity of the design has gone up significantly. Then the to cope with this design turnaround time, this reduced design turnaround time. So, this core based design or this intellectual core based design, so that has become more popular. So, when it is so for designing a system, it is not that we design the whole system together. So, we take the previously designed cores from different vendors and try to integrate them into the system. Now, if I am designing the whole system, then I know which part are important and which functionality of that module is important, and I can design my test pattern set accordingly. And we have also seen several schemes, like we say that the same test pattern may be applied to a number of circuits to reduce the testing time in a broadcast scan mode. Now, when I am taking cores from different vendors, the difficulty that I have is the test patterns are also to be provided by the vendors, because I do not know the internal details of those cores. So, I cannot have my own test pattern set. So, these test patterns are generated by the core vendors, and the core vendors, since they do not know in which environment this code will be placed, so they cannot take help of this say this broadcast scan and all those mechanisms that we have discussed in the process. So, they cannot take help of that. As a result, they try to give as elaborate a test sequence as possible, so that this test so that all the faults in the code are going to be tested. So, this creates a large number of test patterns for the whole entire system that we have. Now, as a test system integrator, so we do not have any other option. So, what we have to do is that we have to apply the test patterns provided by the vendors blindly one after the other and see the responses and compare. So, this makes the whole process very complex, and as we have said that testing process anyway occupies about 60% of this design time. Now with this type of complexities coming in, though the design time has may go down due to this reuse philosophy, this testing time will go up further. So that makes the operation of test engineers more challenging. Second observation that we have is that a circuit or system consumes more power in test mode than in normal mode. So apparently it seems a bit absurd, but in reality that is true, because suppose I have got a system that monitors the temperature of a room. So it senses the temperature values, and depending upon the temperature value, it will be controlling some activities. Okay, it will be turning on some ACs or turning on heaters like that. So it will do something. So the corresponding circuit, so you see it is getting input from some analog to digital converter, which is doing this temperature conversion. Now how does this value changes? Like it is not that in a if you look over a sequence of time, so it is not that the value of the temperature of a room changes abruptly. So it changes in a rather slow fashion. So if it changes in a rather slow fashion, then for the ADC, so if I have, this is the ADC and this is feeding my system. So this is the circuit for temperature control. Now this ADC outputs, so they are also correlated. So if the value was say 1101 at this point of time, then at the next point of time, so it may increase by say 1 bit. So it may become 1110, or it may decrease by 1 bit, becoming 1100. These both of these two values that we have, so they are related. So you see the only these 2 bits they are going to change, but the most significant 2 bits, so they are not going to change. Now this is a circuit where these 4 bits are coming as input. Now so in this circuit I have got these 4 bits coming from the ADC given as input, and out of this, if these 2 bits do not change their values, only these 2 bits change, then a large part of the gates that we have in this circuit, so they will not switch. And we know that in CMOS technology, the power is consumed only when this switching occurs. So in fact this is due to this dynamic power. So in CMOS we have got 2 types of power consumption. One is known as dynamic power, and the other one is known as this leakage power or static power. Leakage or static power. So this dynamic power consumption is coming when the output switches. Like any CMOS circuit, so it can be considered as a P network and an N network. The input is fed to both of them, output is taken from the middle. So N network, this is grounded, and this is the VDD supply. So this is the static CMOS type of design. Now you see that when this output changes to 1, then the capacitor gets charged like this, the load capacitor gets charged like this, and when this output becomes 0, then this load capacitor is discharged like this. But when the input is steady, the either P network or N network is cut off. As a result, there is no current flow through this device. So that way this current is consumed or power is consumed only when there is a switching. That is why in dynamic CMOS, in CMOS, the majority of power consumption is due to this dynamic power, and this power consumption is actually when the switching occurs. So when this switching occurs, if there is no switching at the input, then naturally the circuit gates will not switch. As a result, they will not consume any power. So this is what is controlled here. So we have got in this particular example that we have taken, if these 2 inputs are not changing at all, then it is very much likely that this will not be the power consumption will not be that high. So that is the reason that in case of normal operation of a system, the inputs are going to be correlated to each other. So they do not change much. As a result, they may not consume much of power. However, when we are putting the system into test mode, so in the testing, what is required is that if one test pattern is applied, so suppose going back to the same example, so this is the circuit that I have, I apply the first test pattern T1, okay. So it detects say these 3 faults. Now the second test pattern, if it is similar to T1, then what will happen? So, it will possibly detect say these 3 faults and maybe some more fault or maybe some less fault, that way it will work. But it is very much unlikely that it will detect a drastically different set of faults if the second pattern T1 is very much similar to T2 is very much similar to T1. So, as a test engineer, what we will like to do is that T1 T2 it should be highly different from T1. So, T2 should be highly different from T1, so that it excites some other faults which were not excited by T1. So, that is the expectation. So, in case of testing, what is happening is that these successive patterns that we are having, so successive patterns are highly uncorrelated, whereas for this normal operation, successive inputs are often very much correlated to each other. So, that is why this circuit or system, so that consumes more power in test mode than in normal mode. So, if the correlation is less, that means there will be more number of switching that will occur, because many of the inputs will change, as a result it will consume more power. So, it can give rise to severe hazard in the circuit reliability. So, reliability may be a question because of this power consumption, a good amount of power is converted to heat, and that way it will increase the temperature, and if the temperature increases, then the delay of the circuit will also change. So, if a circuit is not uniformly heated, all portions of the circuit are not uniformly heated, then what is going so the delays of different parts may be different. So, when we are doing a delay test, it may so happen that a chip will fail in delay test, though the chip is actually correct, but due to this heating, this delay differences have occurred, and as a result the chip gets discarded. Or it may so happen that some chip which has got this delay problem, but due to this uneven heating, it passes through the delay test, and a bad chip is being shipped to the customer. So, that can happen. Or it can cause instant circuit damage. If the every circuit has got a power limit, so if that power limit is exceeded, then it will cause a damage to the circuit. Increases product cost, because now I have to be more cautious in my testing process. So, then difficulty in performance verification, and then this reduced autonomy of portable system and decrease in overall yield. So, this power aware testing, if we want to do, then we have to take some special care. So, we cannot test maybe we wanted to test a number of components together to speed up the testing process, but it may so happen that the combined power consumption is crossing the power limit. As a result, we want to restrict that. So, we cannot do that parallel testing. So, that way the testing time will increase. So, that will affect the product cost. Performance verification is in problem, because again the same thing, that is this power aware operation has to come into picture. Portability will reduce, because now the circuit has to be the battery operated circuit, if it is if it has to be tested periodically, and the power consumption is high, for the test power consumption is high, then this battery life is in question. So, this autonomy of portable system, so that becomes less, and as a result the overall there will be a decrease in the yield. So, what are the challenges that test engineers are facing due to these changes, like escalating transistor count, increasing chips complexity while maintaining its size. So, this is always there, because the design is becoming more and more complex. So, these issues will come into picture. Transistor count will increase, then the complexity of the chip will increase, and the chip area is remaining unaltered. So, as a result the density or devices per unit area, so that is going to increase. So, that is going to increase the testing complexity. And also testing is one of the most expensive and problematic aspects in a circuit design cycle. So, as we have seen, we have discussed previously that it is taking about 60% of the time, and nowadays what has to be done is this testing goes in parallel with design, so that both of them go simultaneously. Previously it was done at the end, after the design is over, then the testing process used to start, but now it is not like that, but this is one of the very problematic aspect. So, whatever we have techniques we have seen so far. So, that is the traditional techniques. So, the test methods are evaluated based on area requirement, that is if you are proposing some DFT, what is the extra area that is required. So, if you are proposing some test pattern generation algorithm, then what is the fault coverage that it can produce, then what is the test application time. So, how much time we have to give for applying the test pattern. So, the test pattern set. So, these are the factors which were determining the quality of a testing scheme, or including the architecture and the test pattern set. But these low power systems make power management a critical parameter, because low power systems, so they will have a power budget. So, you cannot go beyond certain power consumption. So, normally the designer will tell the power budget for a system. So, it cannot go beyond that. So, as a test engineer, so we cannot apply patterns so that power, so the budget is exceeded. Okay. So, that way this power management becomes an important part in the testing process also. Why test power is high? First one is that test efficiency correlates with toggle rate. So, this point we have discussed a bit. So, what it says is that if I apply a first test pattern that excites some faults, the next test pattern that I would like to apply, that should excite some other faults, otherwise it will not detect new faults. So, this the pattern that we are going to use must be a totally different one from the existing ones. So, that way this test efficiency, it correlates with the toggle rate. So, that is one very important thing. Then in test mode, switching activity of all nodes is often several times higher than during normal operation. So, the switching activity is actually a measure, like when the system is operating. So, how many times the output changes. As we have seen that for CMOS circuit, this until and unless this output changes, this dynamic power consumption is not there. And till say 90 nanometer technology, so we have got 80% of power consumption of circuit is due to this dynamic power, and rest are due to static power. Of course, with expansion, with the advancement in technologies, the situation is changing. So, now this leakage power is also a very important part of this whole process, and the problem with leakage power is that for about leakage power consumption, so that way part of it will be converted into heat, and that heat for every 10 degree centigrade rise in heat, rise in temperature, this leakage is going to almost double itself. So, that becomes a positive feedback on the system. So, that will be catastrophic. So, that will call a that may cause a thermal runaway. So, we will come to those issues later, but this testing mode, this power consumption minimization becomes an important issue. So, the switching activity of nodes are several times higher because of this requirement, that is in case of normal operation, the successive inputs are correlated to each other. So, many inputs do not change for the module, whereas for this testing part, these successive test patterns, they are highly different from each other. As a result, they will cause this more number of toggles. Often parallel testing is used in SOCs to reduce test application time. So, what we mean is that in a system on chip design, what has been done is that if this is your chip that you are manufacturing, then in this chip we have got different modules from different vendors. Maybe we have got a CPU core from some vendor, a memory core from some vendor, then one IO core from some other vendor. So, these are the different modules that we have. Now, you see that since these modules are not designed by me, so I do not know their details. So, I cannot generate test patterns for them. So, the test patterns have also been provided by the core vendors. Now, so core vendor have said that okay, if this is the CPU, so if you apply this set of test pattern T and if you get this response R, that means the system, the CPU is correct. But we cannot take this description as it is, because if it is a board level design, then the advantage is that you take the individual chips from the vendors, and the vendors, they have ensured that the chips are correct. So, what you need to test is only the interconnect between them. But in this particular situation, what is happening is that we have got only a soft description of the CPU in terms of netlist from the vendor, and that we are combining into one, and on a silicon floor we are going to manufacture them. Now, even if my manufacturing process is 100% correct, so there may be impurities in the silicon. No silicon is 100% pure, so there may be impurities. As a result, the CPU might not have been manufactured, might not have been fabricated properly. So, what is required is that I need to test the CPU even if my manufacturing process is 100% correct. So, that way this testing is required. Okay. So, what we do, since there are each vendor has given me a large set of test patterns, and if I test these individual codes one after the other, so it will take a lot of time. So, we try to do a parallel testing. So, we parallelly test a number of modules, okay, number of codes together, but the as a result what will happen is that in normal operation maybe those codes are not going to act together. So, they are not going to act in parallel. So, even if they are high power consuming codes, the designer will know that okay, these codes are not going to be activated simultaneously. As a result, the power management policy will switch off power for one of them. So, power will be the system power will be within the limit. But as a test engineer, so what we are trying to do, we are trying to test a number of codes together parallelly. So, when we are doing that, then we are going to have the power consumption of all these modules, and if two high power consuming codes are tested in parallel, then we have got this power consumption. There is a possibility that the total power consumption will cross the power budget of the system. So, this is the point that often parallel testing is used in SoCs, system on chip based designs, to reduce the test application time. So, that will increase the power consumption. Then this DFT circuitry designed to reduce test complexity is often idle during normal operation, but might be intensively used in test mode. So, that we have already seen that the scan chain and all that. So, they are actually not active when the circuit is operating in the normal mode. So, then this is only the normal operations are going place. So, there are some error detection circuitry may be there. Then the BEAST that requires this test pattern generator and response analyzer to work. So, those modules are not active in the normal mode of operation of the circuit, whereas for test mode of operation, so they are coming into picture. So, in this test mode of operation, this circuitry that will be activated. So, that will reduce the test complexity, but they will be intensively used during testing. So, if the power consumption of those circuits will cause the overall system power consumption. Correlation between successive functional inputs may be significant, however, for test pattern it is generally kept low. So, this point we have already discussed. So, successive patterns may be input patterns may be correlated, but successive test patterns they are often highly uncorrelated. So, what are the solutions? So, there are some ad hoc solutions. Ad hoc solutions are like oversizing the power supply. So, increase the power supply size, because we need for testing we need higher power. So, maybe we have got a separate power supply for testing. Okay. So, that is one possibility. Then the packaging. So, packaging is an issue, because I have to have some packaging that will be able to sustain the extra heat that is produced. So, that way the packaging may be made packaging may be made better, increasing the cost of the system, and cooling may be there. So, we may have some cooling facility, so that it can withstand the increased current that is coming in the test mode. But each of them have got their problem, like nobody will like to have a large sized battery, okay, for providing the power supply. Then for testing purpose, nobody is going to give us a packaging facility which will be which is costly. And cooling is of course another problem, like so we cannot say that okay, there will be a fan fitted because this chip will become hot during testing. So, for during test we want to cool it, so we will have some fan. So, that is not possible. So, this is one type of solution. Another solution is to insert breaks in the test process to avoid hotspots. So, if the circuit is tested continually, and if one region of the circuit is excited throughout the test session, then what will happen is that that part will become hot. So, that creates some hot spots in the circuit. So, what we do, we break the test session. So, we maybe if total 1000 patterns are to be applied, maybe we apply 100 patterns take a break, then again we apply 100 patterns, take some break. So, that will allow the system to cool down. So, when it cools down, then this static power consumption, leakage power consumption will come down. So, as a result, this test power can be reduced. Then testing with reduced operating frequency. So, this is the other possibility, like you see, you know that the dynamic power consumption that we have in a CMOS circuit. So, this is proportional to V square, the supply voltage, into C into F into alpha, where V is the supply voltage, C is the capacitance that switches, F is the frequency of operation, and alpha is the switching activity. So, if we can restrict these values, so even out of this, the supply voltage we normally cannot do anything, because that is technology dependent. So, it is already done. Similarly, C part, that is the capacitance that switches. So, that is also depicted by the design, because the designer has put the output of one gate going to 10 different places. So, all those 10 gates input capacitance will be seen as the load capacitance of this particular gate. So, as a result, so we have got this C value is also not in our hand. Then this F, the frequency of operation. So, this is one thing that we can reduce. So, we can say that okay, for testing we will do it at a lower frequency, though the actual circuit will operate in the gigahertz range. So, maybe we will be doing our testing in the kilohertz range or megahertz range, and this alpha is the switching activity. So, this is another ad hoc solution. So, we test at a reduced operating frequency. But again, the problem is, if you do that, then all these delay related faults, they cannot be captured. So, these delay faults will not come into picture. So, they will not be detected. So, that is the problem. And we can also do a partitioning of the system. So, we can divide the system into different parts. Okay. So, we can test the system one part at a time. So, that is another possibility. But again, the thing is that how easy it is to partition a system. So, that depends on the system that we have in our hand. So, we need to insert some extra multiplexers and other modules, so that this partitioning can be affected. So, but whether how easy is doing this partitioning, so that remains a question. And test planning. So, test planning is very important, by like when will we test which module, for how much time, etc. So, this has to be planned properly. Okay. So, we will continue in the next class.